All right, it's all set up, I think. Differentiability, part 2. There's a reason these are 2 separate lessons is because there's such a different idea here today. Not difficult, though. Don't get scared. There's nothing really difficult here. This might be one of the easier lessons we've seen in a while, actually. So it starts by saying the numerical derivative. We know that for very small values, the difference quotient, so this is the difference quotient we've been using since last chapter, f at a plus h minus f at a over h. As it sits there, that's the slope of the secant, not the slope of the tangent, because it doesn't have the limit out front. But it says, for very small values of h, this difference quotient gives us a good approximation to the tangent slope at a. Let's make sure we're clear on what we're talking about here. And we'll rewind to advanced functions, sort of, but we've talked about this year. If we've got some curve, whatever curve it is, and I'll do the curve in blue, if we've got some curve like that, and we want to find the slope of the tangent right there, at that particular point, and you've seen me draw a diagram similar to this a bunch of times, because I always sort of draw it the same way. Some curve like this, and we're trying to find the slope of the tangent. Oh, that's too thick. I want a thin tangent so you can really see it there. There's my tangent, drawn not as good as I wanted. Just at that point right there, like that. Very carefully. Like that, yeah? Slope of the tangent. That's what we're trying to accomplish. That's our big reason to be in calculus, is find the slope of that tangent. And what we've been up to since advanced functions is saying, listen, if we take a point out here, and I'll go too far away, even as I draw it, I hope you're thinking, why would you go that far away? And it's just for the diagram. It's just so you can see on the diagram what I'm doing, is we'll hook up those 2 points that we can find, because we've got the equation of the curve, so we can find these 2 points, no problem. And once we find those 2 points, that will make a slope of a secant. Where is it? There we go. This will make the slope of a secant. And as long as you don't go too far out, as long as you don't go too far away, it'll be a good estimate of the slope of the tangent. Can you see in my diagram, it doesn't look that good. This slope doesn't look like this slope. And it's hard to draw. So I draw it far away so you can see it. But the idea is that I'll come in closer here, and I'll actually do a better secant, like that. And you see that that one's a better estimate. And I can keep going like that until I get a really good estimate. Last year we called it 2.1, 2 to 2.1, 2 to 2.01. This year we called it limit as h approaches 0. Get that h really small. So this gap between these 2 points is really small. And if the gap is small enough, now back to the first line here, for very small values of h, the difference quotient gives us a good approximation to the slope of the tangent. As good as you want, actually. Get as close as you want. You want a better approximation? Get closer, get closer, get closer. But there's another way to do it. Another quotient, known as the symmetric difference quotient, and that gets the nice red highlighter, because we have to know when the homework or when the test or whatever says symmetric difference quotient, you got to know what they mean. This one gives an even better approximation. And at first glance, you're like, oh, now you show us the good one. No, this one's got a problem. And I'll get to it in a minute. It's got a problem, but it does better. Because look, back to my diagram here. Oops, back to my diagram here. If instead of just choosing the point of tangency and some point to the right, I could have done way better, and I'll do it in St. John's green. I'll choose 2 better points. And as soon as you see them, you're like, why didn't you just do that to begin with? Because do you see my first secant slope was not a good estimate of the slope of the tangent. I had to get really close first. But if instead of choosing the point of tangency, I choose 1 point a little bit to the left and 1 point a little bit to the right, and you could do better than me. The only reason I went as far as I did was so you could see it on the diagram. But if I go a little bit left and a little bit right, a major aha moment happens. Because when I draw that on, look how close that secant is to the slope of the tangent. And again, you can be angry. You're like, why didn't we just do that the whole time? Isn't it better if we go a little left and a little right. Isn't that way better? It is. Accuracy-wise, it's way better. Way better. There is a problem. And before the lesson's out, I'll show you what the problem is, and then you'll be able to rewind and go, oh, I see why we weren't using this the whole time. It's got a problem, a potential problem. But for now, at this point in the lesson, I'll act like this is an awakening. Like, isn't this way better if we do a secant like this? Instead of going point of tangency and some other point, we just do a little left and a little right, and we get a slope that's much closer to the tangent, much faster. It's much better that way. Now that diagram is all right here on yours, but unless you know what you're looking at, like the diagram just looks like good luck sorting out what that diagram is, unless you've seen it live once, seen me build it. You know, it's the kind of diagram that is not really good in finished form. You really have to see it coming. But that's what this diagram shows. And so this is what we say. Instead of doing point of tangency and a point a little bit to the right or left, we go a little left and a little right. But now the width is 2h. H this way and h that way. So this is the new one, the symmetric difference quotient. Our job today, when is this a good choice and when is it not a good choice? And I think it'll be very clear by the time I'm done. Why? So it says, question for discussion. Does the symmetric difference quotient still represent the slope of the secant? And I want to over-explain that. Yes, but now neither point used is the point of tangency. So we're not using the tangent point in there. We're using 2 points nearby, one a little left and one a little right. So yes, it still is a secant slope. Next, does this limit as h approaches 0, f at a plus h minus f at a minus h over 2 minus h still represent the derivative? And here's the big word. Here's the big mistake I made in the other video of this. Not a mistake. I didn't say it very well. I'll say usually. Usually. And that word should scare you as a mathematician. You're like, what usually? I don't want something that works usually. We better make it clear when this doesn't work. And it's so bad when it doesn't work that often we don't use this one unless we know for sure that we can. Okay? That'll all come details later in the lesson. So usually is the word I want there. Any questions about the setup of this new symmetric difference quotient? Why is it called symmetric? Where's the symmetric part of this? Well, we went a little right and a little left. We did the same on both sides, a little right and a little left. So symmetric, same on either side there. All right. By the way, it could be you're like, I sort of get it, but I don't really understand the calculation that's involved here. Yeah, I know. That's what the examples are for. But do you have questions? I saw a couple of frowns out there. Tell me, is there questions here? Hello. Come in, come in. Yes, welcome, welcome.